This would be the last video in solving eigenvalues, eigenvectors, and eigenspaces for a 3x3 matrix. Now, we're able to come up with characteristic equations of other 3x3 matrices in the previous videos, but I'm gonna leave that for you to try on. And here, this characteristic equation is also a result of a previous video. Please review on that so that you could identify the concepts that were used to come up with this, because it doesn't has this was not automatically given. Okay, this is because our matrix here doesn't have any zero entries, so it's a little bit trickier to come up with the characteristic equation. But since we are the goal is to come up with the eigenvalues, eigenvectors, eigenspaces, so we don't have any options but to really pass through a characteristic equation like this. Here, we are going to solve for specific eigenvalues first, and then corresponding eigenvectors and eigenspaces. But you could see, when we equate all of the factors to 0, our first eigenvalue is automatically 0. But our next two eigenvalues will have the same value. So you have your second eigenvalue is 2, and your third eigenvalue is also positive 2. In short, we have here an eigenvalue of multiplicity of 2. Okay? And in this case, we can see also later one of these two values of eigenvalues, whether it's 0 or 2, that will also create two specific eigenvectors. Okay? But to do that, of course, we will pass through the same process here. Okay, we have lambda I minus a, so we're going to come up with the result of this to be implemented with the specific value of eigenvalues here. But of course, your I here is the 3x3 matrix, the identity 3x3 matrix. So we have this form. Multiply it here, you have 1, 0, 0, 0, 1, 0, 0, 0, and 1. Minus your matrix A, 3, 2, negative 3, negative 3, negative 4, 9, negative 1, negative 2, and then 5. So you will have here this expression lambda 0, 0, 0, lambda 0, 0, 0, lambda, minus you have 3, 2, negative 3, negative 3, negative 4, 9, negative 1, negative 2, and then 5. So this final form of this matrix is actually lambda minus 3, 0 minus 2 is negative 2, 0 minus negative 3 is positive 3, 0 minus negative 3 is positive 3, you have lambda minus negative 4 is plus 4, 0 minus 9 is negative 9, 0 minus negative 1 is positive 1, 0 minus negative 2 is positive 2, and you have lambda minus 5. Okay. This matrix now will then be subjected to this process. The resulting matrix times a certain vector equal to the 0 vector. So we are going to substitute these lambda values here in this expression to come up with this form, but to multiply with a certain vector which will be represented or which will represent as our eigenvectors of the specific eigenvalue. You have x sub 1, x sub 2, and x sub 3 here. And then your 0 vector is of course still in R3, 0, 0, and 0. What you just need to do here is really apply the correct processes in order for us to solve for the specific eigenvectors of the assigned eigenvalues. So the first one here is to use this expression and substitute 0 as our eigenvalue. So the first one is you will have here 0 minus 3, negative 3, negative 2, 3, 3, 0 plus 4 is 4, negative 9, you will have here 1, 2, and negative 5. To be multiplied by x sub 1, x sub 2, and x sub 3, as mentioned here, and equate to the 0 vector of R3. Now, in our previous videos, one of which as well before, we're able to use only analyses because there exist 0 entries. Because if there are 0 entries here, you can look at the possibility of removing one of these three coefficients and automatically give us a result for a specific value of x sub 1, x sub 2, and x sub 3. But here, since we don't have 0 entries, what we need to do here is really to come up with the row echelon form of this. So the first one is if we're going to multiply negative 1/3 to row 1, then you have in your row 1, so this would be a leading 1. So we have here a leading 1, so you have positive 2/3 and negative 1 as you multiply all entries in the first row by negative 1/3. This is still 3, 4, negative 9, 1, 2, and negative 5. So we have here, okay, let's remove this expression first and return it to it later. We will remove this or make this equal to 0. So negative 3 times row 1 plus row 2 to have a new row 2. Then negative 1 times row 1 plus row 3 to become the new row 3. So this is 1, 2/3, negative 1. Negative 3 times 1 is negative 3 plus 3, 0. Negative 3 times 2/3 is negative 2 plus 4, you have positive 2. Negative 3 times 1 is positive 3 plus negative 9 is negative 6. Next row, negative 1 times 1 is negative 1 times plus 1, 0. Negative 1 times this is negative 2/3. This is actually 6/3. So negative 2/3, negative 6/3, you have positive 4/3. Again, negative 1 times this is negative 2/3. This is 6/3, so negative, that's correct. Negative 1 times negative 1 is positive 1 times plus negative 5 is negative 4. Next is to make this 0. I mean, not 0, 1. So you have 1/2 of row 2 for a new row 2. So you will have 1, 2/3, negative 1, 0, 1. This is now negative 3, 0, 4/3, negative 4 here. Finally, to make this, to make this 0, the next thing here is to multiply for negative 4/3 rather to our row 2 to have add it to row 3 to have a new row 3. Let's see what happens next. You have 1, 2/3, negative 1, 0, 1, negative 3, 0. 4/3 negative 4/3 times 1 is negative 4/3 plus this 0. Here comes the process. Negative 4/3 times negative 3 is positive 4 plus negative 4, 0. We have here a row of zeros. This means that we can now safely return here and analyze that since there are no entries here aside from 0, x sub 3 can be assigned as an arbitrary constant. So let x sub 3 be t. Okay? With that, we can now use that for our second equation. You have x sub 2 minus 3x sub 3 is equal to 0. X sub 2 minus 3t is equal to 0. X sub 2 is positive 3t. And with that, on our first, you will have x sub 1 plus 2/3 x sub 2 minus x sub 3 equals 0. X sub 1 plus 2/3 times 3t minus t equals 0. That can be cancelled out. X sub 1 plus 2t minus t is 0. X sub 1 plus t equals 0. So our x sub 1 is negative of t. With this, our eigenvector for our eigenvalue, which is, this is the first eigenvalue, 0, is, you have here x sub 1 which is negative t, positive 3t, and positive t. Factoring out t, you will have here negative 1, 3, and then 1. With this is now our eigenvector, and our eigenspace is a set of t times negative 1, 3, 1, such that t is an element of R but not an element of a set containing 0. Eigenspace for this eigenvector for this eigenvalue. So we only have one here in this case. So our next eigenvalue is positive 2, which is also our third eigenvalue. Since this is the last eigenvalue, we do hope here that this could come up with two different eigenvectors. Okay, so with this, we will use this expression, substitute 2 there. You will have negative 1, negative 2, 3. 3, 2 plus 4 is 6, and you have negative 9. You have here 1, 2, 2 minus 5 is negative 3. Just for this, I would like you to focus on this first before I will continue. This first and the third row are just multiples of the other, because the third row is just negative 1 of the entries in the first row, right? This is also true with this and that row, because this is just a multiple of negative 3. Negative 1 times negative 3 is 3, negative 2 times negative 3 is 6, negative 3 times 3 is negative 9. So we have 3 rows here which are multiples of the other. In this case, we are expecting here rows of 0. And how many rows of 0 are there? Since there are 3 multiple rows of multiple of the other, we're expecting here to only have 1 row of non-zeros. In short, there are 2 0 rows. With that, we are expected to have only one equation and then equal to 0. Okay, that's just analysis. But of course, I'm going to show it to you algebraically here. Okay, as we are still going to target this to become a row echelon form. So please pardon with these spaces here. Alright. The first one is multiply row 1 by negative 1 to have a new row 1. So this is positive 1, positive 2, negative 3 now. See? It will be the same as that. But of course, these are 3, 6, negative 9, 1, 2, negative 3. So we're going to stop, remove this first and add it later as we are done. So here, we're going to multiply negative 3 to row 1 plus row 2 to have a new row 2 to make this 0. Next, we're going to multiply negative 1 to row 1 plus row 3 to have a new row 3 to make this 0 as well. But here comes the change. You have 1, 2, negative 3 here. Negative 3 times 1 is negative 3 plus 3, 0. Negative 3 times 2 is negative 6 plus 6, 0. Negative 3 times negative 3 is positive 9 plus 9, 0. Now we have 1 row of zeros. See? It's still appearing. Next, negative 1 times 1 is negative 1 plus 1, 0. Negative 1 times 2 is negative 2 plus 2, 0. Negative 1 times negative 3 is positive 3 plus negative 3, 0. So we have 2 rows of 0 entries. Now from that, let's return x sub 1, x sub 2, and x sub 3. Equate it to 0, 0, and 0. We only have one equation now. We have x sub 1 plus 2x sub 2 minus 3x sub 3 equal to 0. Right? Now, since we have only one equation and we are to solve for x sub 1, x sub 2, and x sub 3, what we can do here is to assign arbitrary constants to x sub 3. Let's use s since we already used t earlier. And x sub 2 also w. So that we can represent x sub 1 in terms of w and s. So you have plus 2w minus 3s equal to 0. So x sub 1 is equal to negative 2w plus 3s. So using these representations, here comes our vector here for our eigenvalue of 2. We have 2 arbitrary constants, w and s. So we are expecting here 2 different forms of eigenvectors. Please bear with me. X sub 1 is negative 2w plus 3s. Your x sub 2 is w, your x sub 3 is s. To make use of this representation, we can write it like this. Negative 2w plus 3s. And since our second entry is just w, so you can write it as w plus 0s. Okay, or just simply 0. And your s there can be written as 0 plus s. Now you can now separate the two. You will have negative 2w, w and 0, plus 3s, 0, and then s. Okay? So factoring w for the first, you will have -2, 1, and then 0. And for the second, you will have s to be factored out 3, 0, and 1. These are your two eigenvectors for the eigenvalue of 2. Okay, so we have two of them. So nevertheless, we still have three different eigenvectors and for a specific eigenvalue. So our eigenspace now here, we can simply combine them into one. So your eigenspace is a set of w times -2, 1, 0 plus s times 3, 0, 1 such that w and s element of the real numbers but not an element of a set containing 0. These are eigenspace, eigenvectors for your eigenvalue, which is 2. So again, this will be the last video for solving eigenvalues, eigenvectors, and eigenspaces for 3x3 matrix. We also have characteristic equations for other 3x3 matrices on our channel as well. I'm going to leave it to you to solve for the eigenvalues, eigenvectors, and eigenspaces. Thank you very much for watching.